All right, let's talk discontinuities of piecewise functions, okay? So remember that there are three different types of discontinuities in our graphs. There's removable discontinuities, and that would be like if some x value is undefined. And also if maybe it were defined, but it's not equal to the limit at that point, that would be a removable discontinuity. So not equal to the limit as x approaches a of that function f of x. Remember that jump discontinuities are basically just when the left limit is not equal to the right limit of that function, right? So if we take the one-sided limits and they are not equal, we have a limit that does not exist, right? And that means that we have a jump discontinuity. And then infinite limits, remember that's going to be when we have vertical asymptotes. And that's going to be when we have a function over a function, right? And that's going to happen when g of x is equal to 0. That bottom part is equal to 0, which we won't have here. So we're really just going to be focusing today on removable discontinuities and how to identify them, and jump discontinuities and how to identify them. So we have an example down here. This is a piecewise function. We have a quadratic function from basically negative infinity to 0. And then at 0, it changes from quadratic to linear. And then it stays linear all the way to the right beyond that. So if you were to think about this, we have some quadratic function, kind of an upside down because it's negative. And maybe it joins with that function perfectly, connects together to be continuous. Or maybe it comes up and there's a hole there, and then it continues on. So maybe the limit is there. Maybe we have a removable discontinuity of some sort. Or maybe it comes up and is completely separated from that next function at 0, where they kind of don't come together, and that would tell me that we have a jump. So we want to know like which one of these three things is really happening here: continuous, removable, or jump discontinuity. So we have to identify those discontinuities if there are some. So what we want to do is we really just want to focus. We know that quadratics and linears are continuous on their own right, but we want to know if they're continuous when they meet, right? So we're really just talking about where they meet here. So what we're going to do is we're going to basically do two steps, well, three steps. Step number one is find the value of all of those numbers in question. So basically just find f of 2 or f of 0. So really just plug in 0. Now, which one of these am I going to use? Is it true? Let's see, which one of these am I going to use for 0? Is 0 less than 0? No, 0 is greater than or equal to 0. So very clearly, I'm going to be using 0 here in this function, right? Because 0 is greater than or equal to 0. So that tells me f of 0 is just equal to, well, f of x is x, so f of 0, if I plugged in a 0 there, would be 0. So I've actually defined, right, my values. Define those x values. Now that clearly means that it's defined, right? If it were undefined, right, if there was nothing for me to plug 0 into, like maybe that was just a greater than sign, then that would be a hole, right? But right now we know that it's at least defined. So it could be a hole with maybe a floating point. We're not really too sure. So the second thing that we're going to check is we're going to check the left and the right limits. We're going to check to see if the left is equal to the right. So what I'm going to do now is I'm actually going to write the limit as x approaches 0 from the left of our function f of x. And I'm actually going to plug that 0 in. Now, if you were to think about a number line here, let's see. This is going to be less than 0, so to the left and to the right of 0. And I'm going to plug in negative 0 squared plus 1, which is really just 0 plus 1, which is 0. Now let's find the right limit, which is going to be that second function. We're going to plug 0 into, well, 0, right? 0 into x, which is just 0. So what I have here is I have basically the left-handed limit is 1. So if I think about this function, it's going up and it's going to stop at 1 from the left side. And then on the right side, it's going to start at 0. So we can see that as from the left is going up to 1, and then it's stopping and it's jumping down and going down to 0. Okay. We have an open circle on one and then a closed circle on the other. That clearly indicates a jump. Okay, so let's just kind of take a look at what this graph actually does look like. This is the graph. Let me erase these kind of markings out of the way. This is what the graph would actually look like if I were to graph it out by hand. So clearly we can see that there is a jump here, but we won't have the luxury of having this graph in front of us. So we have to know that since the limit, the left-handed limit at 0, of f of x, make sure to name the function, is not equal to the right-handed limit as we get to 0 of f of x. Since those two limits are not equal, since those are going to two different numbers, there is a jump discontinuity at x equals 0. Okay, so what our real objective here today is to really identify these things, identify these discontinuities up here by being able to kind of evaluate certain values in our function. In this case, I was evaluating at 0 to make sure it was defined, which it was, and to make sure that the left and the right were equal, which they weren't. And since that was the case, that told me it was a jump. And notice how I included that entire justification down here. All right, since the left and the right limits were not equal, there was a jump discontinuity at that point, which in this case was x equals 0. Okay, let's take a look at another example. Here's another example with 3 different functions. So if you were to get a visual here, we've got a linear all the way up until -1. And then at -1, it changes to a different linear function. And it's going to continue to be linear between -1 and 5. Then it changes again to a different linear function. We have a negative to a negative slope to a positive slope. So the question is it like, is it all connected? Is it all continuous? Or, perhaps there are some different, discontinuities in there. I don't know. That's what we have to figure out. So let's just kind of keep in mind here our definitions of discontinuities, right? Removable, jump versus what have you, infinite. Okay, so let's just take a look. The first thing we're going to do is we're going to find the defined value. We're going to look at -1 and 5 itself. So let's actually find f of -1 and see what that's going to give us. And then we're going to find f of 5. Let's see what that gives us. So we'll start with -1, and we'll just go highlight over here what I would plug in. So let's see, at -1, would I plug in -1 here? Well, let's see. For this first equation, I'm going to be going up until -1, but not include -1 because it's -1 is not less than -1. And for the second equation, we're going to be between -1 and 5, but we are going to include 1 there, right? So if you think about plugging in -1, that is equal to -1. So we're going to be using this equation right here. So let me go over and actually do that math. We're going to do 4 minus -1, using parentheses to show that I plugged in a -1 because now I have a minus a negative, which turns into a plus. 4 plus 1 is 5. So f of -1 is not only defined, f of -1 is 5. Now let's actually find f of 5. Let's highlight this in pink. Okay, we actually had to find out now what we would plug f of 5 into. So 5, let's see. We could maybe, let's see, this function is used, this middle function is used between -1 and 5, but not including 5, right? Just less than 5. 5 is not less than 5. 2x minus 11 is used only when we're greater than 5. So we don't include 5 there or there. So what we have here is we basically have 2 open circles at 5. So that tells us that f of 5 is undefined. Now this is actually beautiful for us because what we're going to do is we're identifying and classifying all discontinuities of that function. This tells me we have a discontinuity right here. So what kind of discontinuity would result in an undefined value? Well, that would be a hole, right? So we know a removable discontinuity or a hole exists at x equals 5. I'm going to abbreviate here because I'm writing on my mouse pad because g of x is undefined. I'm just realizing I had a typo there. At x equals 5. And my typo was over here, I put f of -1 and f of 5, but I should have had g in here because our function is g. Not a big deal as far as like just mathematical computations go, but we should be correct. How we do this. Okay, so we know that since g of 5 was undefined, that there is a hole. So I've kind of stated where it is, what it is, and why I know that. Okay, so I've done all 3 pieces there. I've identified, okay, where, classified what, and I've justified how I know that. So think of those as 3 distinct actions that need to happen in this problem. So now let's see, there's still this -1 in question. We know there's a hole at 5, but we still have to check -1 because even though it's defined, we have to make sure that the limit is the same as the defined value, and that the limit still exists. So for step 2, think about this as step 2, we're going to find the left and right limits, right? At -1. So let's see, we've got to the left of -1 is here, right? And then to the right of -1 is here. If we think about a number line with these functions like the two-dimensional view, we've got -1 and 5 is kind of like our dividers of functions. To the left of -1 is going to be this -3x minus 7. And between -1 and 5 is 4 minus x. So when I'm talking about the left-sided limit of g of x, what I'm going to be plugging in here is this -3x minus 7. And I'm just going to plug in that -1 there. Okay, and in this case, I get, let's see, -3 times -1 is +3 minus 7 equals -4. We found the left-sided limit. Now let's do the right. Let's find the right-sided limit to see if we have maybe a jump or removable discontinuity or what's happening. Got g of x there, and we're going to take the right-sided limit. And in this case, let's see, where's our right-sided limit? That's to the right of -1. So that's going to be that 4 minus our x value. So our x value is still going to be -1. We're going to see what that gets us to. And that's the same function that we used up above. That's going to be 5. Okay, so even though g of -1 was defined and it was 5, and the right-sided limit was 5, we can see that the left-sided limit was not. And we can see here that we have two distinctly different limits from the left and from the right. So what does that tell me? Is that good? Is that bad? Well, that's going to tell me a discontinuity, right? That from the left and from the right, since they're not meeting, there's a gap in between them, which signifies a jump. So we're going to say that. We're going to say that there's a jump. Forgive me for not writing incomplete sentences. At x equals, what was I determining there? -1 was what I plugged in. Because, and we're going to justify with our limit notation, the left-sided limit of g of x is not equal to the right-sided limit at -1 of g of x. So since those two limits are not equal, we would have a limit that does not exist, which really tells us that we have a jump discontinuity. So you'll see a couple of key moves in here, a couple of really kind of big points of emphasis. Two things that I'm squaring in right here are my answers, because remember, it tells us to identify. Let's make sure I did that. Let me pull up a new pen. Identify. Did I identify them? Yes, at -5, at x equals -1. Did I classify them? Full and jump? Yes. Did I justify my answer, my reasoning? Yes, with the limit notation. Okay, I talked about why that was. So this is what you're looking for today. You're going to go through and you're going to try to find those different types of discontinuities, and you're going to identify those types of discontinuities and justify your reasoning. Get to that assignment. This is a huge one. This is a big one. This is one that will come up continuously. Let me know if you have questions. We can always set up office hours. Also, thanks for being here.